Hello everyone. I hope you all are fine and having a great time. Welcome back to the Fundamentals of Plastic Deformation lecture. Today what we will be doing is basically, according to the plan, we will be working on additional topics and examples on tensile test. And what I would like to do is I would like to build on the previous lecture which we carried out. And before I do that, so let's have a quick slight background. So today what we want to do is we want to do more of the application side of tensile tests rather than learning more about theory. So you already know your facilitators, and as we discussed the last time, so we are here at the part 2, process dependent basics, and specifically we are here determination of the flow stress and modeling of the yield stress. So we are on the so now we are from the theoretical side, we are slowly moving towards the experimental side, and on the application side of the material models and how do we want to use them. We are also slowly broadening our perspectives into the area of how we can use them for our applications, and today's lecture is basically more on that area. Just to have a quick background, so last time what we did was we established the fact that we want to have materials which absorb more energy, and how do we calculate that, and then other material attributes and properties, and how can we get that data from very simple tensile tests, and how to carry out tensile tests, and how is the information recorded, and how is it post processed, and so on and so on. And we reached at a conclusion where I shared a specific file with you for processing and so on. And today I would like to start with this very beautiful and very to the point script from Yuval Noah Harari's book 21 Lessons for 21st Century. And in this book he states that he initially what he describes is that nowadays it is an information age, and in the information age everything is only one click away, and people are being bombarded with a lot of information all the time. And then he states this, that in such a world the last thing a teacher needs to give her pupils is more information. They already have far too much of it. Instead, people need the ability to make sense of information, to tell the difference between what is important and what is unimportant, and above all, to combine many bits of information into a broad picture of the world. And it is such a powerful quotation from which he has captured specifically here, and this is what I see all around. So whatever we are teaching here in these lectures, you can always find the bits and pieces here and there on YouTube and in other books and in other lectures and from other subjects and other departments. You probably would have studied about them in your bachelor's degrees, and you would have an idea about the tensile tests curves and so on from different angles and different aspects. But I feel that now you're in a phase of bridging the gap between the applied science and then the development of and then research and development. So the master's program is a bridge between both, where you come from application side to the invention side, and then you start developing rules and principles and algorithms and information for the people who can apply it in their worlds. And this is, I feel, very important key position where you have to generally understand the concept of things, and then you have to understand how they're being applied and how you can make them simpler and easier. So today, by starting with this very beautiful quotation, we will come back to from where we stepped out last time. In the last lecture, in the end, I explained that the tensile testing of SS316L sheet was carried out using standard ASTM E8 standard. I also shared this standard with you all. I would just quickly would like to know that how many of you went back, downloaded this standard and read it or tried to go through it. I've started a poll, you can vote. That's great. So I see that 13 of the 32 people have voted, and most of the students didn't download and go through the standard, whereas almost 20% of the students did. When you are not voting, I presume that you didn't do that. So almost 20% of the students did. Now, going through this standard, downloading this standard and going through this standard is important, because then you are not just on the theoretical side, but you realize how challenging and difficult a very simple test or a very simple task becomes when you want to standardize it. And what are the challenges involved, and what are the solutions given, and then whatever you read in the theory, how it is being applied on a global standardized scale. So even if you have not downloaded it or went through it yet, I would highly recommend that you please download it and go through it, so you have a better understanding. And you can make sense of what we are teaching here in theory, how it is applied in actual life. And then, for example, the next thing is that I would like to publish these results. And then what we did was that we stated that we have this sheet which is 0.5 millimeter thick and has a certain width, which was 25 millimeters or I don't know, 12 millimeters, and that made it cross-sectional, then made this cross-sectional area of 6 millimeter squares. And then we have this gauge length of 45 millimeters. And with this data, I shared an Excel file with you. And we started off with that Excel file last time. And what I wanted you to download that Excel file and perform certain actions on it. So the very basic thing which we did last time was calculate engineering stress strain, and then initially plot force displacement curves, clean up the data, and then calculate engineering stress strains, and then post-process the data. So we got a curve something like this now. And then the next step was to calculate true stress strain. And I would like to ask how many of you have calculated true stress strain and you have the files with you right now? Because this is the starting point of where we would like to continue today. And this is the application side of everything you read in the theory and all the formulas and everything which you read on the slides. And this is where you will make sense of how to use that information actually. And I think this is a very fundamental, very basic, but very important kind of an assignment which every student should just be able to do in seconds. Okay, so I see that 4 out of 33 or maybe even more students did that, and 30% didn't. So almost 10 said no, but only 14. I have only 14 votes, so I presume rest of the students. Oh, okay. Can you please tell again how to remove negative values from data? Interesting. You just select the negative values and press delete. That is how you remove the negative values. I don't know if that is what you're asking. Okay, I will publish these results, and what I would want you to do is can you please briefly explain what was discussed in previous lecture, as some of the students including me was considering that there is no lecture in previous week, and why were you considering that? I don't know. So in the last week as well, I had almost this many number of students attending the lecture. I also recorded the lecture, so I can share that with you later somehow, but it would be difficult to repeat it because I will always have limited time and so on. But if you were not present in the previous lecture, what you can do is you can go on Opal. Let me see where. Yeah. So you can go in your Opal course, and there you can go in lecture manuscripts, extra data, and here you can download this Excel file, which is tensile test data.xls. And when you will open up this file, you will see this work which we did last time. And this is where I want to start from. Okay, so we already have, so when you will open up this file, you will already have an engineering stress strain curve. And what I want you to do now is to calculate true stress strain and plot it again in Excel. How will you do that? For calculating true stress and strain, the formulas which you have already studied in the course are given here. Once again, for your reference, please use this and calculate true stress and true strain in that Excel file. And you have 5 minutes to do that. Let me start a clock. So it is 4:12 right now. 4:13 almost. You have time until 4:18 or 17. 4:17. So I would suggest that everybody downloads this Excel file, opens it up, and tries to process this data and fill these columns with true stress and true strain. And then we will have an interesting assignment to make. And then also, if you calculate that, please plot it here as a true stress strain curve in a separate figure as well. Just to continue with the discussion which we had last time, I would like to start a poll with an information about how many of you know how to use Excel for calculating such formulas. And if you don't know how to use Excel for calculating such formulas, then can you also write me privately or publicly if you are comfortable? Then how do you calculate these? So maybe you use another software or another tool which I don't know of, or something like that, so I have an idea of how you're working with such calculations and plotting of the data. Okay, so time's up. How many of you were able to calculate true stress and true strain using these formulas given here? And yeah, just calculate. So 2 said yes, 3 said yes, 2 said no, and the rest. If you're voting no, I would like to know why. If you can inform me about that, I would have an idea of what to explain and how I can help you with that. Please, I don't know how to use the formula on Excel. Okay, fair enough. But you don't know how to put a formula in Excel, but you are familiar with Excel, so you have installed it and you can open up this file in your computer. Is that correct? Okay. Okay, so I will publish these results. Let's go back to the file, and basically this is not part of this course, so it should be this is a complete new tool. It requires much information and much background knowledge to have a basic understanding, but just to apply this formula, which is, if I want to calculate true stress, I have to multiply engineering stress with 1 plus engineering strain. So in my case, this is engineering strain, this is engineering stress in the file given, and then the true stress would be equal to engineering stress multiplied by 1 plus engineering strain, and I will get this value. And to use this formula, which is true strain is equal to log of 1 plus engineering strain, I have to use formula log of 1 plus engineering strain, and we get these values. So basically what it does is it multiplies it and then writes it here, then goes to the next columns, multiplies them with the formula given and writes them here, and then I have this complete list. And what I can do is I can quickly just copy this, so we have homogeneous figures. I can add a title here, chart title, which is engineering stress stress strain, and then we can also add a title here. True stress strain, and what I can do is I can select new data for this. So true strain is this, and true stress is this. And if I go here, I can just remove this, and I get this curve. Okay. Now you might not see a big difference here. So what I can do is I can rename it true curve, and I can rename this as engineering curve. And then what I can do is I can make a new one and put these two on the same graph and see the results. Legend. Okay, so this is comparison. So now you will see a clear difference between true stress strain curve, which is higher, and engineering stress strain curve, which is lower. Is that clear? I would really appreciate if you can use this process and calculate your own values, because the next assignment is associated to that. So was that understandably clear? And now you see that we have the same data set. We have same machine data, force and displacement. And then what we are doing is we are converting it into engineering strain and engineering stress by using the information which is given on this slide here, cross-sectional area and gauge length. And then we plotted this engineering stress strain curve, and then we use the formulas given here on this slide for calculating true stress strains. And then we calculated true stress strains, we plotted them in a separate curve, but then when we put them on the same graph, we see that there is a slight difference. So all the theory comes to this point. So was it understandable until now? I would like to know. And if you are voting no, then I would like to know why, so I can explain it, because the next part is associated with these calculations, and that is important. Again, when you are voting no, I would like to know what was not clear and what should I explain more so you can follow it. Okay, super. So I see that it is clear for most of the students. Now, what we have done so far is we had machine data, which was calculated using this standard ASTM E8, and then we calculated engineering stress and engineering strain. We have those curves in the file, and you probably would have calculated it. And what I would like to know is what is the value of Young's modulus for this material? Can you calculate that? I would like you to write the answers in the comment section so we can compare the results. So we would like to do all these calculations step by step. So what is the value of Young's modulus for this material? Our question is, how did you do the calculation? The question is not very clear. It is quite vague. On the previous slide, I have shown how I did the calculation. So if I come back here, and there are quite many easy ways of doing it. So one way is to divide stress with strain. Yeah. The other possibility is to see the slope of this line, and that is what I will do here. So that is a graphical way of doing it. We can quickly do it here. So no. So what I will do is Young modulus. And then what I want to do is I want to clip the data in the elastic range, let's say until this point, which is 244 of this. So until here, which is cell 15. In it, cell 15. What? Yeah, okay. So we have this here, and then what I want to do is, so this is almost a straight line. What I want to do is I want to add a trend line, yes, and then I want to display the equation of the trend line. And this value with x is basically the slope of this line, which we call Young's modulus. So from the current data, we get Young's modulus of 142 349 megapascals, because this value is in megapascals, and if I converted it to gigapascals, it would be 142 gigapascals. So the Young's modulus is Young's modulus of this material is approximately 140 gigapascals, and this is quite interesting. Okay, I would like to know how many of you were able to calculate that. One person was not able to calculate that. Okay. And if you were able to calculate that, was your value close to what I calculated here, or was it different? As one of the students mentioned that some people from you were not present in the previous lecture. So I would like to repeat. I don't know if you know about the examination which came last year, but we believe we slightly changed that, and this year we want to continue that, and we believe that the students participating in Fundamentals of Plastic Deformation course who are studying very rigorously the material properties and how they originate and what are their uses should at least be able to calculate them from the machine data and then process them to calculate these values. So this is something which was part of an examination last semester. We are not sure if it will be how we will check this knowledge of students this semester, but because if the examination is online, then you can very easily make such an Excel sheet and can submit it with your solution, and it is very easy to mark that if you have a general idea of how to calculate these values and how to post-process the machine data, and or generally understand from a stress strain curve how to calculate Young's modulus and so on of different material attributes. So it is important for you to follow this lecture and also participate, because if not, these are the very basic fundamentals now. So I don't know, it will be hard then. Can you please show again how import the line equation? Stress strain value, do I need to take the average of all the values? If I am using stress strain value, do I need to take the question is that if I calculate it using the stress strain values, do I need to take average of all the values? I don't think so. So this is basically a technical question, and there can be many solutions to this problem, but one of them is that we take the trend line, and trend line is always the average of all the values, and then we just plot an equation which is very quick and easy process in Excel, and then we can quickly use that. So here as well we are basically generally taking the average as well. The other question was, can you please I hope that answers your question. If doesn't, you can write it again and I will clarify. Can you please show again how import the line equation? I'm not importing. Okay, so this equation. Okay, so let me delete this, and what I'm doing is I have selected this trend line, and then a side panel appears if you have Office 2013 and above, and then you can select quickly display equation on chart, and when you do that, an equation is displayed on chart, and if I select R values, it also shows me by the regression analysis that how compatible this trend line is with the actual curve. So it is almost 98% fitting. This is how you bring this equation on the chart. Okay, interesting. So then let's come to the next question, which is what is the value of yield stress? And this is quite interesting. So how do we calculate yield stress? Now comes the problem if you have already went through this ASTM E8 standard or not, or if you are following the lectures. We also state that the yield stress in such a material where there is no Luder band, there is continuous yielding here, is at 0.2% of the plastic strain. So where does plastic strain start is also always a tricky question. So what I would like to do here is I would like to copy this here, and then we would like to see where plastic deformation is starting in the material. I have total of 413 points. Okay, this would be interesting. So from, let's say, make it 20 and make it 20. Okay, so I see that elastic region is here until this point, which is 0.0010, 0.0010, and it was point number 10. And if I change this, if I change this, the elastic limit changes, and now my Young's modulus is also slightly changed. It is not 140, it is now 160. So it depends on what area of the curve I am considering. But now I know that my elastic range is ending until this point. So what I would do is I would change this value. I would start it from the elastic range and end it here. I would start it from an elastic range and end it here. Okay, so this was the elastic part, this still is the elastic part. Let's go slightly higher, 0.0017, 0.067. Okay, so it is 0.80. Need it. Point 80. Huh? Zero 0.015. So this is 0.13. Okay. What I'm doing is I'm just trying to find the remove the plastic curve from here. Yeah, okay. Elastic curve from here and just see the plastic curve. Now what I want to do is I only want to calculate plastic strain. And what is this? It is 13, this one. So it is after this. And what I want to do is I want to subtract this value from all the rest of the values so I can get my curve back to this point. So normalize it with respect to this point. How I'm gonna do it? I'm gonna do it by is equal to this minus this, and then fix this. Okay, so I will take this curve, and instead of this strain I will plot this strain, and instead of this, yeah, the stress is same. I will continue with this, and now we get this we call this flow curve, because it only consists of the plastic part of deformation and not the elastic part of deformation. And now we want to see where 0.2% of the total deformation occurred. Is that correct? Let me check the standard again. Stress strain diagram for determination of yield strength. Yeah, so 0.2% of the total strain occurred now. So the total strain in this material is what is this value? 0.08. So 0.2% of 0.08 is 0.0016. So I have to see where 0.0016 is. So here, and the corresponding stress for this value is 305.44. So from here we say that oh, okay, let me delete this. So yield strength of the material is 305 MPa. Is that correct? 0.0016, yes. So yeah, 305. Okay, super. So this is flow curve of the material. Yeah, so this is how we are calculating the yield stress of the material. And then what would be the ultimate tensile strength of this material from this curve? Can somebody quickly tell that? So if I just quickly go back and look at the previous slides. So here we have, yeah, so here we have all these values now. So when there is continuous transition, which is our current case, the ultimate strength is the maximum force, the maximum stress which the material undergoes, and that is basically this value, which is around 513 MPa. So I will copy this and so basically what we do is we do not calculate ultimate tensile strength on the true stress strain curve, but rather the engineering stress strain curve. So if I use this here, then engineering stress strain curve, and then I can just quickly copy this here, and I can write UTS of the material is almost 472 MPa. Yeah, so the answer was 500 MPa. Yes, it is close. Generally, the maximum force which the material undergoes is the maximum stress which the material undergoes before the necking begins is the ultimate tensile strength of the material. So yeah, it is this value. And then the next question is, what is the total elongation of this material? And what is the total elongation if we measure it in percentage or strain? I would want you to calculate that in right here while I answer this question, which is, I do not understand how you find yield point. Okay, so in the last lecture, I don't know where that is. Yeah, so in the last lecture, we studied that if our material undergoes continuous transition, then this value of engineering stress at 0.2% of plastic deformation is called yield point. And I just did this in Excel, and this is how. So I removed this part of the curve, I converted it into a flow curve, and then just saw where and then calculated how much was the actual strain in the material, what is the 2% of that strain, and then just saw the point at which 2% of the strain occurred, and that was my yield point. It is 0.2%, not 2%, because we want to see just when the material starts to plastically deform. So it is always 0.2% of the total elongation, not 2% of the total elongation. If you will go in the standard here, it is also clarified here. So yield strength is, it is given for an example 360 MPa, but it says that offset 0.2%. I don't know. Yeah, so offset method. Yeah. Okay, so what is the total elongation in the material? That is something which I would like to know now. That is quite easy. It is not that hard. If you have this Excel file, you should be able to answer that. From the engineering stress strain curve, we have maximum strain of 0.08, So that is the total elongation. So if I multiply that with 100, we have almost 8.69, 8.7% of total elongation. So what I can do here is total, or I can just copy this and put it here. Total elongation in the material is almost 8.7%. Okay, super. Then I would like to continue with the next part of the lecture, which is from these curves which we have already plotted. What I would like you to do is to calculate strain hardening, total work done, and point out the start of necking using one of the formulas. I think it is hard to calculate to point out the start of necking using this data set, but the other two can be done quite easily. So it is important that we do this as well. But before going there, what I would like to do is I would like to quickly share with you this YouTube video, which is generally specifically explaining all these things in an experimental way, so you can imagine, so it is easier for you to imagine what is happening here. I just want to quickly know if you can listen to the audio. Super. Super. Okay. I hope this was interesting and explanatory, and would have generally clarified how the machine is working, and then again how we are measuring the force and displacements. And what we are doing in our sheet is basically the next step of processing that data. Yeah, so the Excel sheet which I shared with you, where did it go? Here, which I shared with you earlier in the first lecture. Basically, this is the data which we get from the machine running time as well, but generally this is the data which we get, which is force and displacement data from the strain gauge. And then what we are trying to do here is we are trying to post-process the data and calculate all that, all the important information there. Okay, so most of the students say it was helpful. There is one student which says it wasn't, and then I would like to know why it wasn't helpful, so I can explain it more. Anyways, what we want to do now is we want to calculate hardening and total work done. So this is also something which we studied in the previous lecture. So if you come to, I don't know which slide was that. So we already studied this concept. Yeah, so this was the one. So the ideal work done would be volume of the material versus the total stress and total strain, and that would give us the actual work done when we calculate it on the actual material. So if I calculated for my material, then it would be basically I will have to measure the volume here. So the volume which I have is 6 millimeter square cross section area into 45 millimeter gauge length, and that comes out to be 45 multiplied by 6 is 270 millimeter cube. And I would like to use the not the millimeter units but the meter units, and then it would be, what was that? It was 270. So it is 270 E minus 9. Yeah, so meter cube multiplied by true stress multiplied by true strain, and the value of true stress is in megapascals, so I would like to multiply it with 1e6, so convert it into pascals. True strain is okay, and then what I would like to do is I would like to put brackets around it so there is no confusion, and then divided by 1e3. What? Oh, okay, sorry. I need a bracket here, and then divided by 1e3 to calculate work done in kilonewtons. And this is it. What? It is too small. I'm messing up the units. This is in meters, this is in pascals, and then if I do not divide it by 1000, then we are getting a certain value. And if I so this is basically the area which is under the curve, and I can plot it on a certain graph. We can plot it here. Chart design, select data, add work done, and then I am using the x values of true strain and the y values of work done, and then what I'm doing is I need to put it on secondary axis. Yeah, so this is the total amount of work done. I have to add axis titles, and now this is true strain, this is true stress, and this is actual work done. And this is also something which we saw in our previous lecture, I think here. Yeah, so this is specific deformation work, which was Newton millimeter per millimeter cube. So basically the units are disturbed and the values are quite high. And if I see it, so if I have a flow curve like this, I have a work done curve which is going straight up because we are accumulating the total amount of work done. And if the flow curve is relatively lower, then we have this work done. And when we see the work done curve for our system, it is also an almost linear curve going up. So this is basically the total area under the curve which is required to totally deform the material up to this point. And then what we also want to calculate is we also want to calculate strain hardening, and this is also quite interesting because what we do here is we calculate the differential. And what I will do here is I will not start the formula from here, but I will start the formula from here, and is equal to true strain this minus, let's say, this this divided by what is divided by this minus this, and this will give us a very low value. Let me move it on the other side. We should get very high value, and then we should be slowly going. Yeah, okay. No, next one minus previous one divided by this one gives us a nice value which is close to 0. I don't know, hardening is on the true scale, is the slope would be linear. Okay, so one way of doing it is this, and the other way of doing it is that if we use this plastic flow curve, this one, and what we do is we plot these both on logarithmic scales. Okay, and then I also plot this on the logarithmic scale, and then I add a trend line, and then okay, so this needs to be on a certain scale. But for example, then if I add, oh no, this is a complete mess. But yeah, the general idea is that if I have both on the logarithmic scales, then basically the trend line, the slope of the trend line is basically the hardening of the curve. The other possibility is to calculate it using this change in strain over change in stress, and then we get this value. What I would like to do is, we still have some time, so what I would like to do is give you an opportunity and possibility to calculate all this data from the Excel sheet which you have, and if you have any questions you can ask here. I will be willing to answer them while I search for an option of calculating strain hardening. class we uploaded an opal in the last week class thinking there was no class due to behate. Yes, I recorded the last lecture as well, and yeah, I can share that with you in the future. Change in stress, interest rate, or change in stress. Change in stress into strain divided by this multiply by, and then we can do this, and voila, we have this value which is fluctuating too much, but I understand that. Okay, so basically we have experimental data and therefore this value is changing too much, but I can plot it here, and now I understand why we are getting that, but hardening, and then what I can do is true strain from here onwards, and then hardening is from here onwards. And this should be a non-logarithmic value, and this as well should be a non-logarithmic value, and this can be from -1 to 1, okay, to 2, and we see this variation here, but generally a trend line would be in between this, so I basically cannot calculate hardening from this data because this data still needs to be cleaned. So when so it becomes quite sensitive when I want to calculate this formula, but generally, yeah, we can calculate hardening by either using this method or by either using this method, and this would give us a value which will be between 0 and 0.3, 0.4, somewhere here. For example, for steel, this value is around 0.2 or 0.15, somewhere here, no? So yeah, yeah, so if you have any questions you would like to ask, I would be happy to answer them. Otherwise, thank you very much. This was I feel that it is quite an important and interesting lecture to take and understand, and understand what is tensile testing and how we process its data to get these results. In the next lectures, Dr. Irani will continue with flow curves and additional topics of flow curves with you guys. So yeah, I will try to share this recorded lecture on the Opal as well. Could you please share this Excel file? Yes, very interesting. I can. Let me just quickly close this. Let me stop